Thermostats, an example of control systems by Chase Ginther and Sean Kelly.
Throughout the course of this presentation, we will first give a brief introduction into the purpose and history of thermostats.
Following the introduction, we will discuss the overall home heating control system and the role a thermostat plays in that system.
Next, we will detail the approach we took in modeling and simulating how a home heating system will operate.
Finally, we will summarize our conclusions and take any questions the audience may have.
Simply put, a thermostat is a temperature-sensing control device that is used to maintain a desired temperature or set point.
In almost every home, a thermostat is used as a temperature-sensitive switch that will automatically turn on the furnace or air conditioning to maintain the wanted temperature inside the house.
In newer homes, programmable thermostats are being used. This updated technology allows the thermostat to adjust the temperature in the house depending on time of day.
When used in car engines, as a certain temperature is reached, the thermostat will open, allowing for the flow of coolant throughout the engine. By controlling when the coolant flows, it allows the car to reach temperature as quickly as possible, reducing wear and emissions.
When people think of thermostats, many picture the round Honeywell models that have been around for decades, but it was over 100 years earlier when the first one was invented.
In 1830, Andrew Ure, a chemist from Scotland, invented a bimetallic thermostat that worked by bending as the temperature rose. As the bending took place, it opened the circuit, effectively cutting off the power supply from the heat source.
In 1883, Warren Johnson invented an electric device that would ring a bell when the temperature reached a certain point. He created this device due to the inconvenience associated with going to the basement to inform the janitor that his classroom was getting too cold.
2 years later, a much different device was created by Albert Butz, an inventor from Switzerland. His device, called the damper flapper, worked by opening and closing a furnace door with automatic pulleys in an attempt to regulate the temperature. Butz was also credited for helping pave the way for Honeywell, who in 1953 released the world's most recognized round thermostat.
When it comes to home heating systems, they can be considered as a process control system. The purpose of this particular system is to maintain a set home temperature regardless of outside temperature changes or heat loss through the walls and windows. The control signal sent from the thermostat travels to the furnace fuel valve, which allows for combustion in the furnace. The heat created by the furnace then travels throughout the house to a temperature sensor located inside the thermostat. When the desired temperature is read by the sensor, the thermostat then turns off the signal, thus completing a cycle of the process.
In order to mathematically model a home heating system, it is helpful to first create a block diagram. The block diagram is made up from the components or subsystems within the heating system. The first step in building the diagram is identifying the components. In this case, we will be working with a heater, a thermostat, the house, modeled as one room for simplification, the outside environment, and the inside environment.
Going from left to right, the first system modeled is the thermostat.
The constant block feeding into the thermostat is the temperature, in Celsius, that would be chosen on the dial or digital display. The subsystem consists of the input of the set room temperature into a summing block. The output of the summing block feeds into a relay which acts as an on-off switch for the heater. The second input into the summing block is the monitored room temperature. The purpose of this subsystem is to turn on the heater at a certain temperature and turn off the heater at a certain temperature.
The second subsystem is the heater. When the output on the thermostat reads that the heater needs to be turned on, the information travels into the heater switch. The measured room temperature goes into another summing block along with the set heater temperature, which is 50 degrees Celsius. 50 degrees Celsius is a reasonable running temperature during the spring or fall. The summing block of the heater temperature and the room temperature output gets fed into a heat gain block. The heat gain block multiplies the difference of the two temperatures by the mass airflow rate through the heater and the heat capacity of air at a constant pressure. This value is then transferred to the heater switch. The outcome or output of this subsystem is the heat gain.
The final subsystem in the block diagram is the room. The room subsystem includes a summing block. The input of the summing block is the heat gain and the calculated heat losses caused by outside temperatures. The measured outside temperature is put into the negative side of the summing block. The temperature of the room is then put into the positive side of the summing block. The output of the summing block is fed into a gain block to multiply the thermal resistivity to calculate the heat loss. This is then fed into a summing block that subtracts the heat loss from the heat gain. The output of the summing block is transferred to a gain block that multiplies the input value by the inverse of the mass of the air inside the room multiplied by the air capacity of the room. When this value is entered into the next integrator block, it gives us the change in room temperature. The room temperature is continuously fed into the Simulink loop to either turn the heater on or off.
The top two signals are measured inside and outside temperatures. The measured outside temperature was used in the Simulink model. As you will see in the temperature comparison chart, the measured inside temperature was used in the simulation.
In order to perform all of these functions, a few different formulae were needed to complete the calculations. In addition to specifying room parameters, the following heat transfer equations were needed as well: rate of heat gain, rate of heat loss, and rate of inside temperature change.
Now that the modeling is complete, we were able to run a simulation of how the system cycles during a 24-hour period using outside temperatures comparable to spring or fall in Pennsylvania.
As you can see, the measured room temperature varies from approximately 20 to 24 degrees Celsius. After being adjusted for hysteresis, the simulated room temperature fluctuates proportionately, only without the noise from the skewed results. The outside temperature is shown to reach as low as 5 degrees Celsius during the morning, rises to 20 degrees Celsius midday, and then drops back down in the evening.
In conclusion, the temperatures in a heating system are monitored and regulated by the thermostat. Not only are the indoor temperatures regulated by the thermostat, but the amount the heater runs is also regulated. In order to control the amount of time a heater runs, the set point could be chosen closer to the outdoor temperatures.
As the temperatures rise around 10 a.m., the measured indoor temperature slowly rises due to less excessive heat loss than what takes place during colder temperatures. The simulated room temperature shows that the indoor temperature during the warmest part of the day stayed at the 20 degrees because there was no heat loss during this time. The measured indoor temperature continues to rise due to the residual furnace heat combined with the rising outside temperature.
To show you how important a thermostat is in a heating system, let's look at an example. If the thermostat was not included in the heating system, you'd have to manually operate your furnace every time you wanted to change the temperature in the house. This could prove to be far more costly and hazardous, in addition to taking up valuable time. Thanks for listening.